So what we have shown is any distribution function is always non-decreasing, it is right continuous, fx of minus infinity is 0 and fx of plus infinity is 1. Now using advanced mathematical arguments, it can be shown that any function g which satisfies these three properties, what are those? Non-decreasing, right continuous, g of minus infinity is 0 and g of plus infinity is 1. So any function which has these properties is a distribution function of some random variable. One has to show this using construction, that means you have to show a probability space corresponding to which g is a distribution function of some random variable defined over there. So I will not go over there, I will not discuss that. So what I will assume for the time being is any function which has these three properties is a distribution function of some random variable. Now those who have done a basic calculus, they know that any monotone function is either continuous throughout. Now if it is not continuous, then it can have at the most countable number of discontinuities. And since distribution function is monotone, it says that any distribution function is either continuous on R or has only countable number of discontinuities. So either distribution function will be continuous or at the most it can have countable number of discontinuities. So very important property of distribution function. In fact, this is a property of any monotone function. Let us try to see. Fx of x minus 1 is always less than or equal to fxx, and we have seen that fx is right continuous, so this is same as fxx plus 4 for every n. So I take the limit, limit always exists because it is a monotone sequence, because fx is monotone. So limit n going to infinity, fx of x minus 1 by n is less than or equal to fxx is equal to fxx plus. So which is equivalent to saying that this is nothing but left hand limit of fx at point x. So fx x minus is less than or equal to fxx, which is same as fxx plus. So one very nice property about distribution function is its left hand limit and right hand limit exist at every point x. It is always right continuous, so right hand limit is always same as the value of the function. So that means the only way discontinuity could occur is that fxx is strictly bigger than fxx minus. So now let us try to see what is the probability x less than x, which is same as px of minus infinity to x. Now note that minus infinity to x can always be written as union of these events. So what is happening is you have figure like this, x is over here, x minus 1 is over here, x minus half is over here. So what you are doing is you are moving like this. You can go as much closer to x as you wish, but you will be never able to touch x. And since x is not included in any of these sets, so this union is going to be minus infinity to x. Now if you look at this sequence, this is an increasing sequence. So px of union is same as px of limit, and px being monotone because every probability function is continuous. So this is same as limit n going to infinity px of minus infinity to x minus 1 by n, because this is a monotone sequence and the probability function is always continuous. But this is same as limit n going to infinity of fx of x minus 1 by n, which is same as fx of x minus. So what it says is probability x less than x is same as fx of x minus. So if you have to find probability x less than x, that would be same as fx x minus. Note that by definition of a distribution function, probability x less than or equal to x is same as fxx. So probability x less than x is same as fxx minus. That is what we have shown just now. So probability, now let's try to see if a is less than b. So a is over here, b is over here. So then probability x less than or equal to b is this event. This is same as union of two disjoint events, which is probability x less than or equal to a, union x lying between a to b. And they are disjoint, so that is why this probability would be same as the sum of these probabilities. Probability x less than or equal to a plus probability x greater than a less than or equal to b. A is included over here, that is why you have a strict inequality over here, and you want less than or equal to b, that is why less than or equal to b is over there. So what you get is probability x greater than a less than or equal to b is same as probability x less than or equal to b minus probability x less than or equal to a, which is same as fxb minus fxc. So what you get is probability a less than x less than or equal to b is same as fxp minus fxa for every a less than b. Now to see what is happening probability x a less than x less than b. This would be same as probability x less than b. From this you have to subtract x less than or equal to a because it is greater than a. So equal to a has to be on the complementary part. So x less than or equal to a, which becomes fxb minus because probability x less than b is fxb minus probability x less than or equal to a is fxa. Similarly consider probability a less than or equal to x less than or equal to b. This is same as probability x less than or equal to b minus probability x less than a, which is same as fxb minus fxa minus. Now let us consider this. This is same as probability x less than b minus complementary of this, which is same as x less than a, probability x less than a, which is fxb minus minus fxa minus. Probability x greater than b is same as 1 minus probability x less than or equal to b, which is same as 1 minus fxb. Probability x greater than or equal to b is same as 1 minus probability x less than b, which is same as 1 minus fxb minus because probability x less than b is fxb minus. So probability x equal to x is same as probability x less than or equal to x minus probability x less than x, right? Because x equal to x set can be written as x less than or equal to x minus x less than x. So the probability of this would be same as this probability minus this probability. Probability x less than or equal to x is same as fxx. Probability x less than x is same as fxx minus. Let dx be the set of discontinuity points of fx. Since fx is always right continuous, because any distribution function is always right continuous, so I know that x is a discontinuity point if and only if fx minus is greater than 0, which is equivalent to saying that probability that x equal to small x is positive. Thus, a distribution function has only jump discontinuities, that means fx minus is greater than 0, and the set of discontinuity points is nothing but collection of all those x belonging to R such that probability x equal to x is positive. So let us consider this example. So suppose x is a random variable which has this distribution function. So let us try to see whether this is a proper distribution function or not. So what are the properties I have to check? Fx is non-decreasing. Clearly for x less than 0 it is 0. From 0 it goes to x by 3. I have to check where it changes. It changes at 0. At 0 it remains 0. And then x by 3 is an increasing function, so it remains increasing throughout. At 1 again it changes. It changes from 1 by 3 to 1 by 2, which is increasing. So it increases, and half is a constant, so it is non-decreasing between 1 and 2. 2 again it changes. It changes from half to 2 by 3, that means 0.5 to little more than 0.6, so onwards, so which is again increasing. And then it remains constant between 2 to 3. At 3 it changes from 2 by 3 to 1, which is again a jump in the positive direction. So it is non-decreasing. It is right continuous because x by 3, half, 2 by 3, 1, 0, such functions are continuous. So the only points of discontinuity could be 0, 1, 2, 3. Let us try to check at 0. At 0, I have to check only the left hand limit is whether same as value of the function or not. At 0, left hand limit is 0, value of the function is 0, right hand limit is also 0. So at 0 it is continuous. At x equal to 1, right hand limit is half, value of the function is half, so it is right continuous. At x equal to 2, value of the function is 2 by 3, right hand limit is also 2 by 3. At x equal to 3, value of the function is 1, and right hand limit is also 1, so it is right continuous. Fx of minus infinity is covered over here, which is 0, fx of plus infinity is covered over here, which is 1. So it is a proper distribution function. Let us look at what are the points of discontinuities. As I said before, I have to check only the points where it is not left continuous, because right continuity we have already verified. At 0, left hand limit is 0, value of the function is 0, so at 0 it is continuous. At 1, left hand limit is 1 by 3, right hand limit is 1 by 2. So 1 is a point of discontinuity. 2, left hand limit is half, value of the function is 2 by 3. So 2 is also a point of discontinuity. At point 3, left hand limit is 2 by 3, value of the function is 1, so 3 is also a point of discontinuity. So dx is 1, 2, 3 and so on. Now one has to check what is the probability x equal to 1. Probability x equal to 1 we know is same as fx1 minus fx1 minus. You can check fx1 is same as 1 by 2, fx1 minus is 1 by 3, so this turns out to be 1 by 6. Similarly, probability x equal to 2, which is same as fx2 minus fx2 minus. fx2 turns out to be 2 by 3, fx2 minus is 1 by 2, so this turns out to be 1 by 6. Similarly, probability x equal to 3 is same as fx3 minus fx3 minus. fx3 is 1, fx3 minus is 2 by 3, so this turns out to be 1 by 3. Probability x less than 3 is same as fx3 minus. fx3 minus we have already seen is 2 by 3, so it is 2 by 3. Probability x greater than or equal to 1 is same as 1 minus probability x less than 1. Actually, this is same as 1 minus probability x less than 1. But probability x less than 1 is same as fx1 minus. So this is same as 1 minus, fx1 minus is 1 by 3. So this turns out to be 2 by 3. Now suppose C is not any of the point 1, 2, 3. That means it is not a discontinuity point. So that means C is a point where fx is continuous. So probability x equal to C would be same as fxc minus fxc minus, because it is continuous at C, so it would be 0. So probability 2 less than x less than or equal to 3 is same as fx3 minus fx2, which is 1 minus 2 by 3, which is 1 by 3. Probability 1 less than x less than 2, which is same as probability x less than 2, which is fx2 minus, minus probability x less than or equal to a, x less than or equal to 1, which is fx1, fx2 minus fx1 minus is 1 by 2, minus 1 by 2, which is 0. Probability x1 less than or equal to x less than 3, which is same as probability x less than 3, fx3 minus, minus probability x less than 1, which is fx1 minus. fx3 minus you can see is 2 by 3, fx1 minus is 1 by 3, so this turns out to be 1 by 3. Now probability 2 less than or equal to x less than or equal to 4, which is same as probability x less than or equal to 4, which is fx4, minus probability x less than 2, which is same as fx2 minus. So this turns out to be 1 minus half, it turns out to be half. Now let me give this quiz. So let x be a random variable with this distribution function. So if x is 0, if x less than 1, 1 minus 1 by x, if x is greater than or equal to 1. One can check that this is a distribution function. Let S be the set of all natural numbers. So find the value of probability x belonging to S. You take this as a quiz. Now take home problem. Let G be distribution function of some random variable, so that Gx minus is always less than or equal to Gx is less than or equal to Gx plus. This follows from the fact that distribution function is always monotonically non-decreasing. Now similarly, if x is less than y, try to show that Gx plus is less than or equal to G of y minus. So they are simple to prove, just using the fact that G is monotonically non-decreasing. Now let fx be continuous on R, so that means your distribution function is continuous at every point. So probability x equal to C would be 0 for every C. And let S be any countable set, so that probability x belonging to S is 0. In fact, I have given you the solution, in the sense that if it is continuous, then probability x equal to C would be 0 for every C belonging to R, and from that you can conclude this. Now let me give the abstract of the next module before I conclude. Now what we have seen is, if you have a distribution function, the set of discontinuity points of fx is collection of all those x's such that probability x is equal to x is positive. And we've seen that this is a countable set, because set of discontinuity points of a monotone functions is at most countable. Now there may be situations where probability x belonging to dx is same as probability x equal to x is 1. So that means there may be situations where the whole weight is given to discontinuity points in dx. So that means this probability function p gives whole weight, which is the weight 1, to the discontinuity points. Now we'll call such random variables as discrete random variables. So in next module, we'll study the properties of a discrete random variable. First we'll introduce the discrete random variables, then we'll study the properties of discrete random variables. So that was all for this module. Thank you very much for your patience and have a great day.